Welcome to the Exploratorium and Countdown to Mars. I'm your host, Ron Hipschman, and in the next hour or so, we're going to follow along as the Perseverance rover lands on Mars. We are going to do a lot of stuff here today. We're going to be able to peek into mission control, and at about 12:38, when things really start speeding up down there, we'll switch to them, and I'll try to translate a little bit, listening in. So hopefully our 7 minutes of terror will go really well today. More on that 7 minutes of terror later. Here's the schedule for today's events. At 12:38 our time on the west coast. The cruise stage will separate. It'll enter the atmosphere about 10 minutes later, experience peak heating at 12:49. The parachute will deploy about 3 minutes later. The heat shield will separate 20 seconds later. The back shell will separate, and the sky crane will rocket its way down to the surface at 12:54, and rover touchdown is scheduled at 12:55. So before 12:38, we're just going to talk a little bit about the Mars mission for you. So we hope that you enjoy that. If you are interested, if you'd like to follow along in real time, be sure to visit the eyes.nasa.gov website. Just click on the Mars 2020 and you'll be able to see in real time. As a matter of fact, let's put that up right now. Here you see in real time what's going on. We see the Mars spacecraft there attached to its cruise stage with the aeroshell in front there, heading towards the planet. In about 38 minutes, that cruise stage will separate, and we'll watch that happen. Now, Mars we've sent many missions to Mars. We've sent actually about 60 missions to Mars. Not us, the US, the world actually. And of those, in red, there are 27 failures, or about 48% of the missions. 3 partial failures in yellow, or about 5%, and 21 successful missions in green and blue. Only 46% of the missions have been successful. The U.S. has been lucky with about 75% success rate. The last missions you see here on this list with a black background have either just arrived or are future missions. This week has been really busy on the red planet, with no less than 3 missions to arrive there. Just on February 9th, the United Arab Emirates, UAE, has successfully placed in orbit their first Mars spacecraft named Hope. Hope's mission will be to explore the global weather and climate of Mars. A huge congratulations to the UAE for an amazing feat of putting something in orbit around Mars. It is really hard to do. We look forward to seeing that atmospheric and climate data in the future. Also, the next day, on February 10th, China delivered its first mission to the red planet. This mission, called Tianwen-1, consists of both an orbiter and a rover. Its mission will be to search for evidence of both current and past life, similar to Perseverance, and assess the planet's environment. They're going to attempt to land the rover in May. So we also congratulate China for their success, and we look forward to seeing their data as well. Today, we're going to be talking about Mars 2020 and the rover named Perseverance. Perseverance is going to be landing today, as I mentioned, during our webcast. Mars 2020, which was renamed, the rover was renamed Perseverance, was launched July 20th and will be landing today, the 18th, 2021. Like Curiosity, the previous mission, its mission duration is designed to last for 1 whole Martian year, which is about 687 sols, or Martian days. The Martian day is a little bit longer than an Earth day. It's about 687 Earth days is the entire mission for Perseverance. Just a note, Curiosity, which landed August 6th, 2009, 2012. As of today, has been operating for 3,118 days, Earth days, and it was only, of course, designed again for that 688-day mission. So it has been a wild success. It's lasted for 4.5 times its mission duration, its intended mission duration. Perseverance launched again on its journey July 30th, 2020 from Cape Canaveral. I always love watching. If you ever have a chance to go to Cape Canaveral, be sure to go and watch a launch. They are absolutely amazing to go and launch. I've had the privilege of watching 2 shuttle launches from there, and it's really an amazing thing to go and see. It'll take Perseverance 203 days to travel its 293 million miles from the Earth to Mars. And during this mission, it can perform up to 6 target correction maneuvers, or TCMs, to keep it on track. Initially, it was set to miss Mars when on launch, and that's because the probe, the aeroshell and the cruise stage are being tracked, followed by the second stage booster all the way from Earth. And since the second stage booster has not been sterilized as much as the lander itself, they don't want it to hit Mars, and so it's set to miss Mars. So during the mission, during that TCM 1, 2, 3, and up to 6, they can target the Perseverance spacecraft to hit Mars exactly on arrival. Its target is Jezero crater, which is kind of in a fairly equatorial location. You can see the landing spots here of NASA's other successful missions. We're going to take a little bit closer look here at now Jezero crater, marked with the little dot there next to Perseverance. Jezero crater was formerly filled with water, creating a very large lake, about the size of Lake Tahoe. This photo is falsely colored to emphasize the height of the terrain. Lighter color green and yellow colors are higher terrain, and darker blue colors are lower. The black ellipse marks where Perseverance will be landing. That's the landing ellipse. It can land anywhere within there, but they hope to be a little more accurate than that. The lake itself, it had a large inflow channel, and it has a large outflow channel that you can see here. That's how they know there was water in there at one time. Let's look closer at the inflow to the lake. We see a large delta right there that was formed by sediment that's entering the lake. And this is a likely place to find preserved fossilized microbial life, if it ever formed there. We want Perseverance to land right next to the delta, right about there, if possible. Within Jezero crater, Perseverance will explore the crater floor, and then it will ascend the delta, moving into higher and higher, and hence younger and younger terrain. If the mission lasts long enough, Perseverance will explore the crater wall. To talk about the main mission of Perseverance, I'd like to introduce Julie Yu, Exploratorium Senior Scientist.
One of the great unsolved questions in science is whether or not there is life somewhere else in the universe. Now, one question to ask yourself is, if there is, how would we know? What would it take to convince you? It may seem straightforward to identify what's living. For example, you and I are alive, but this sheet of paper is not. So how do we know what to look for if we're looking on another planet? Now, scientists don't all agree on how to define life, but NASA uses a very specific definition, and that is a self-sustaining chemical system capable of Darwinian evolution. Now, there's a lot packed into that one sentence, so let's try to break it down a bit. By self-sustaining, we mean it's able to reproduce on its own. It can make copies of itself. Chemical system means it can undergo chemical change. An example of that is metabolism that gives us our energy. Darwinian evolution means a lot, but the key point here is that there's some sort of information, such as a genetic code, that is inherited and has variation. That variation allows things to evolve and adapt to changes in the environment around them. So how do we test for that? Now, it's hard to notice evolution happening in a given moment, so it's a little more straightforward to test for the chemical system. That is, are there chemicals present that participate in the reactions that are essential to life as we know it? And are there molecules that might support the biological information transfer, such as the carbon-based ones that make up our DNA? Now, one place that scientists have been looking for these things for over 45 years is Mars. Why Mars? One of the main things that people look for in planets that might support life is the presence of water. On Earth, liquid water is essential for life. So if water's present, that planet might have the possible chemistry to sustain life. Now, there's actually no liquid water present on Mars. It's too cold and dry. Water there is either present in the form of ice or water vapor. But Mars wasn't always that way, and there's evidence that once upon a time there was liquid water, and that liquid water might have provided the environment to sustain life. So we've seen pictures of Mars. There's nothing there that's going to come up and introduce itself to us. So the type of life we're talking about is ancient microbial life. That is life that's probably too small to see with our naked eye that lived a long time ago. Our next big chance to test for this life is when the Perseverance rover lands on Mars. Now, all of the past Mars missions have had some experiments to test for possible life, but this is the main goal of Perseverance, and it's fully outfitted with cutting-edge equipment to do these tests. Its landing site has been specifically chosen to be able to test different geological areas that might have had water, and it has brand new cameras and sensors that'll be able to describe the chemical composition of the surrounding area and detect whether or not there are molecules that might support life. One final goal of Perseverance is to investigate the potential for future human exploration on Mars. Mars's atmosphere is mostly carbon dioxide. Can we make oxygen up there? How will spacesuits hold up in the Martian environment? All of these things will be tested. So even if we're unsuccessful at determining whether or not there was past life on Mars, it's possible that through Perseverance, we will be able to show that Mars can indeed sustain life by going there ourselves.
Oh, thank you, Julie. By the way, if you get a chance to view any of Julie's other amazing videos, go to our YouTube channel and check those out. As Julie told us, the mission of Perseverance is to search for signs of past microbial life and to examine the geology and the weather of Mars. The Perseverance rover has a drill on its arm that can collect core samples of the most promising rocks and soils. It's an extremely complicated and versatile roving laboratory. Perseverance, as I mentioned, has a unique set of tools. The camera on the mast also has the ability to send out vaporizing laser pulses to analyze rocks and soil at a distance. This helps to determine which rocks the scientists should have a closer look at. At the end of the arm is a drill that can take a core sample of solid rock. It can both turn around as a normal type drill, and it can also act as an impact drill. The core sample it takes is a solid piece of rock or maybe gravel. Here you can see it drilling down into the surface, bringing that core sample back in and depositing it in a carousel inside the rover. That carousel will carry the sample tube down to a robotic arm. And that robotic arm will take it over to a place where several functions will be performed on the sample. It'll have the sample's volume measured. They'll seal the sample tube, and they take pictures of the sample at each step. And then it takes that sample tube and it moves it into storage. Perseverance carries about 43 of these tubes. Not all of them will be used for samples. Some of them will be left as control tubes to make sure that we didn't take any biological material to Mars with us. So this had to be ultra sterilized. Eventually, the collected core samples will be left on the surface of Mars for a future mission to come and collect them and return them to Earth. Perseverance will gather these samples from a whole variety of places, and it'll return them to a centralized collection point. The future Mars sample return mission will dispatch a small rover that'll go out and collect these samples left behind by Perseverance. It'll collect all of these samples using a small arm to collect them off the surface. It'll place them in a little sample holder on the rover and then bring them back to a lander. This is a solar-powered rover, notice, and its wheels are not solid like the wheels on Perseverance and Curiosity. These are metal mesh wheels, much like the lunar rover had during the Apollo missions. It'll bring those samples back to a rover which has its own mechanical arm, which will then take the samples and deposit them in a container. This is a prototype of that special container inside the lander that will protect the samples on their return flight home. This sample container will be placed into a very small rocket, and that rocket will launch from the surface of Mars into orbit around the planet, where it will meet an orbiter. Here's our small rocket. It will disgorge the sample container, and the orbiting satellite will then capture the samples. Now, inside of that satellite, the samples will be captured and further packaged into a much more protective container. And that container is then placed into an aeroshell, which has a heat shield in front, and that heat shield eventually will protect the samples as they return to Earth. Then the orbiter will fire up its engines and leave Martian orbit and head back to Earth. As you can see, this is a really complex mission. It'll take several months for that orbiter to come back to Earth. When it gets into the vicinity of Earth, the aeroshell, with its heat shield containing the samples, will be ejected onto its final path towards Earth. When it enters the atmosphere, it will form a fiery meteor, hopefully protected by that heat shield with the precious samples inside, landing eventually, a soft landing recovered on Earth. Now today, we're going to talk about the beginning of that whole mission. We're going to talk about Perseverance. And what we're experiencing today is the entry, descent, and landing, or EDL sequence. Perhaps the best way to see these is in action during the EDL procedure, but I have a slide here just to show you. NASA calls this whole procedure the 7 minutes of terror, at least for the mission operators. This technology was the same as was used for Curiosity in 2012. Desiree Whitmore, our senior physics educator, will take us through the complicated and, well, in my opinion, rather audacious landing procedure.
One of the most important and most stressful parts of any Mars rover mission is the landing phase, which is commonly referred to as the 7 minutes of terror. Hola, my name is Dr. Desiree Whitmore, and I'm a physicist here at the Exploratorium. Where does the name 7 minutes of terror come from? Well, 7 minutes refers to the time that it takes for the Mars rover to enter into the atmosphere, descend, and land on the Martian surface. This is called the entry, descent, and landing, or EDL phase of the mission. Because the Earth is so far away from Mars during the landing of the rover, it takes 11 whole minutes for any signal to reach the Earth from Mars. This means that we will not know for sure if the rover has touched down until 11 minutes after it has happened. So what goes on during these 7 minutes that could possibly have NASA engineers so worried? Well, first of all, the spacecraft has to slow down all the way from 12,500 miles per hour all the way down to 0 miles per hour in a height of only 80 miles. Second, the rover has to land inside of a crater that is full of obstacles like cliffs and rocky terrain, all without a driver. Luckily, NASA has landed previous rovers on the Red Planet and has learned a lot each time and has continued to make improvements. The spacecraft itself is made up of 5 main parts. At the top is the cruise stage, which carries the fuel tanks, the solar cells, and other tools necessary to travel to Mars. Below that is the back shell, which contains the parachute. Beneath the back shell is the descent stage, which will help the rover with its final landing. And then you have the Perseverance rover itself. And on the bottom, you have the heat shield, which protects the rover during entry. Around 10 minutes prior to entering the Martian atmosphere, the craft separates from the cruise stage and leaves it behind. It's done its job to get the craft to Mars, and now it is just extra weight. The aeroshell, which is made of the heat shield and the back shell, spends the next 10 minutes positioning itself just right for maximum slowdown upon entry. The best position for entry is to have the heat shield in just the right angle so that the most molecules from the atmosphere will hit it as it travels. These molecules will push up against the heat shields, which introduces a drag force and helps to slow it down a lot. It starts at a speed of 12,500 miles per hour, and the drag force will slow it down all the way to 1,000 miles per hour, which takes about 4 whole minutes. Now, all of these molecules pushing against the heat shield also creates friction against it, which causes it to heat up a lot. The heat shield reaches a temperature as high as 1,300 degrees Celsius, which is hot enough to melt iron. But the rover, which is inside of the shell, only gets up to about 25 degrees Celsius, which is about room temperature here on Earth. Because the atmosphere on Mars is so much thinner than the atmosphere on Earth, there's not enough drag force exerted on the shell to slow it down to land. We need something that is able to introduce much more drag force. Once the shell slows down to around 1,000 miles per hour, which is about 1.7 times the speed of sound, or Mach 1.7, the aeroshell can deploy its parachute. This is the largest parachute ever made at 70 feet in diameter. This is the first mission where the timing of deploying the parachute is left completely up to the rover, based on its position relative to its target. It has a new technology called range trigger. This will give the rover a much smaller area to land in, free of obstacles, and will help to reduce the chance that it will overshoot or undershoot its target, cutting down its time to commute to work site by as much as a year of precious mission time. 20 seconds after the parachute is opened, the heat shield is dropped, which allows the rover to start taking data using its radar and camera systems. The brand new Terrain Relative Navigation takes photos of the surface of Mars as it is traveling, and it compares them to maps that are already on board its computer to better understand where it is and to make course corrections. The jetpack and the Terrain Relative Navigation work together to get the rover to its target location, making sure to avoid any obstacles that could be in the way of descent. When the descent stage has reached an altitude of 65 feet, it is now time for the sky crane maneuver. The jetpack can't get too close to the ground because it will kick up a huge dust cloud, which could ruin the rover and all of its instrumentation. So instead, it lowers the rover down on a 20-foot rope to the ground. As soon as the rover begins lowering, it uncurls and locks its wheels in place for landing. Once the wheels are firmly on the ground, the cables are cut and the jetpack flies away as far as it possibly can to protect the rover, and it crashes into the Martian surface once it runs out of fuel. All of this will happen in just under 7 minutes, and we on Earth will be waiting for an additional 4 minutes after landing to hear back that the rover has even entered the atmosphere so that we can learn about the fate of the rover and whether or not its landing was successful.
By the way, the impact of those things on the surface, they're going to try to observe from the insight lander, which has previously placed a seismometer on the surface. Now, I think we should talk a little bit about the communication that Desiree talked about. She mentioned that JPL has no control over what happens during the landing because of the 11-minute delay of the signals from Mars to the Earth. Let's take a look at that. Once Perseverance arrives at Mars, it's quite far from Earth, and at the speed of light, 186,000 miles per second, it takes the signal from the spacecraft 11 minutes and 22 seconds to get to Earth. And that's why mission operators on Earth won't know if Perseverance has landed safely, and why later on in the mission they can't drive the rover around using a joystick. It's a huge delay. It's a 23-minute delay of the signal, Earth to Mars and Mars to Earth, that makes driving the rover that way impossible. The rover has an autonomous system on it that allows it to drive by itself in a limited sense. The mission operators decide where to go, and Perseverance decides how to get there. Much like autonomous cars will work here on Earth, hopefully soon. Like Curiosity, Perseverance has 3 antennas it can use to send data. Although Perseverance can send data directly to Earth with its high-gain antenna, that takes more power, and the data rate would be slower. It's more efficient to send data to a Mars orbiting satellite with its low-gain antenna, with its UHF antenna rather, the one that's kind of shaped like a paint can there, and then have the satellite relay data to Earth with its more powerful transmitter. An orbiter like the Mars Reconnaissance Orbiter can relay the signal directly to Earth with its more powerful transmitter. MRO has been reprogrammed actually to relay the signal without any delay. And this is called the bent pipe method of communication. I'm sure you can see why they call it that, but it still takes over 11 minutes for that signal to arrive at Earth. Mars 2020 carries an interesting passenger. Attached to the underbelly of the rover is a helicopter. That helicopter is designed to fly in the very thin atmosphere of Mars. The helicopter is named Ingenuity. It doesn't really carry any scientific payload itself, only a couple of cameras, one pointing directly down at the ground for navigation and one pointing more at the horizon so that we get to see some pretty views. Within a month of landing on Mars, Perseverance will deposit Ingenuity on the surface and then back away about 100 meters. Notice it has solar cells on the top so it can recharge itself between flights. First, it's going to do a little exercise to make sure that its rotors turn properly, like you just saw there. Ingenuity has also a small antenna that will be able to transmit the data back to Perseverance. Perseverance is going to observe the flight with its cameras as well. Now, Ingenuity is a technology demonstration that NASA believes could be useful on future missions to provide forward scouting or be able to give information and do some science where it's inaccessible to the rover or even to astronauts on future missions. There you can see Perseverance following with the camera. The first flight will be just up and down, and it will make a maximum number of flights only in the first month of Perseverance's mission, and then Ingenuity will be left behind. There you can see the 2 cameras underneath that can snap pictures of the terrain. It will never venture very far from Perseverance for this mission. But when it's done, it will head back and land somewhere near the rover. The rover is still following it with its cameras. Once Ingenuity lands, it will transmit its data back to the rover, and the rover will transmit the data to a satellite, to MRO or one of the other Martian satellites, and then back to Earth. Now, I want to talk a little bit about some of the science on Perseverance. Perseverance carries 7 scientific payloads, and these are some really interesting ones. Let's take a look at where they are on the rover here. They're literally attached all over the place, and they all have, of course, the usual acronyms that NASA is so famous for. Let's just take a look at a few of them. We have about 8 minutes until the cruise stage separation. I think that gives us a little bit of time. I don't know how far we'll be able to actually go here with the experiments, but we'll break away as soon as there's some action on the spacecraft itself. For us, one of my favorite things is the Mastcam-Z. It's a pair of next-generation science cameras on Perseverance's remote sensing mast or head. This is a pair of zoomable cameras. That's different than Curiosity. Curiosity's cameras couldn't zoom. And these are going to be used to shoot video and create high-resolution, color, stereo, 3D panoramas of the Martian landscape in multiple different colors. There's color filters on these cameras as well. Here's a picture of the cameras removed so you can kind of get a look at what they look like outside the rover. The images will help rover operators drive and position the rover's arm instruments, and analysis of the landing site's geology viewed with Mastcam-Z will help scientists determine the history of the landing site region as well. Here's a model that was used just for, you get a feel for the size there. They're located again on the mast of the rover, and you notice there's a little science package with a little post near the back side of the rover there. That's actually used with Mastcam-Z, and it's a sundial. It looks like this. The sundial needs the two Mastcam-Z cameras need calibration targets, something to look at where the colors have been calibrated in the lab. And these calibration targets have been made part of a traditional part of Martian rovers, the sundial. Sundials have been on all Martian rovers so far. Here you can see the gray and colored targets around the dial. The sundial motto is 2 worlds, 1 beginning, which refers to the idea that Earth and the red planet grew out of the same proto-planet stellar dust. Besides the motto and swatches, the sundial displays a small line of early life forms, line drawings of early life forms on Earth, including cyanobacteria, a fern, and a dinosaur. There's also a man and a woman, similar to those on the Pioneer plaques and the golden record on the Voyagers. It's all a tribute to Perseverance's astrobiology mission. Another instrument on the rover is called MEDA, which stands for Mars Environmental Dynamics Analyzer. Again, I'll try to get the acronyms here for you. It's a set of sensors distributed over Perseverance's mast and body that measures wind speed and direction, air pressure, relative humidity, ambient temperature, basically the weather on Mars, and solar radiation. Here, let's take a look. Here you can see the 2 wind speed and direction sensors underneath the cameras there. They're sticking out from the mast. Here's a little movie of the deployment of the sensor. Slow-mo. That's the wind sensor with sense wind speed and direction. And again, they're located on the mast. There's another package there you'll notice on the deck of the Mars, of Perseverance, and it's a SkyCam. SkyCam measures how tiny airborne particles or aerosols, aerosols such as dust and ice can affect sunlight reaching the surface of the planet. Very important to determine. SkyCam again is located on the deck of the Perseverance rover. Now MOXIE stands for Mars Oxygen ISRU Experiment. This is good. Not only is it MOXIE an acronym itself, but the acronym contains an acronym, and that ISRU is an acronym for In Situ Resource Utilization. MOXIE converts carbon dioxide in the Martian atmosphere into breathable oxygen. It does this very slowly. It's, again, a technology experiment. The rover itself does not need any oxygen, but for future human missions to Mars, it may be important to be able to convert CO2 from the Martian atmosphere into oxygen to supply not only humans for breathing, but also for fuel for rocket engines to be able to take off from the Martian surface. Here's the actual package itself. It's kind of, again, not inspiring to look at, just a box. And here they are kind of lowering it in to the body of Perseverance. It sits just below, near the base of the body itself. There you can see its position, sort of midship there. Another interesting experiment is called PIXL, or Planetary Instrument for X-ray Lithochemistry. It's located at the end of Perseverance's robotic arm, and it's going to be used to measure the chemistry of the surface and help search for signs of ancient microbial life in rocks. It's kind of a lunchbox-size instrument located on the end of Perseverance's 7-foot-long arm, and they'll be able to position it against the rocks on the surface with this little stage, which is can move in 6 axes. Really cool little instrument here, instrument platform. It's located again on the instrument arm itself. We have still have about a minute and a half here before we. Actually, let's go ahead and switch to our simulation here, our visualization. See where we are. So here we are approaching Mars. It's, I have 12, 36, and 40 seconds right now, so in about a minute and 20 seconds. The cruise stage, that flat cylindrical solar cell covered part of the spacecraft, which has gotten the spacecraft all the way to Mars, will be separating from the back shell of the spacecraft, and that will give us once that happens, we'll switch back and I'll talk a little bit about some other, actually maybe we'll go to our control room and see if they've received signals about that. That should happen again at 12:38 in about 45 seconds. Let's switch to the control room and see what they're saying right now. Do we have any audio from the control room? Let's see. No audio yet.
It's about 10 minutes from cruise to separation till entering the top of the atmosphere. From then on and out, things happen fast.
Switching to MFSK tones. Telemetry will have stopped.
Telecom is confirming that the spacecraft has switched to broadcasting tones. These tones are received directly from Perseverance, but have very limited information content. We won't receive real-time information until about 9-10 minutes from now, once the Mars Reconnaissance Orbiter starts relaying information from Perseverance. We are under a minute from cruise stage separation, about 10.5 minutes from entry interface.
So in about 30 seconds, we should see the cruise stage separate from the back shell.
You're seeing the heartbeat tones.
Okay, that means that there's no more ones and zeros coming. It's just the vehicle telling us it's still alive.
We're continuing to receive tones from Perseverance, standing by for cruise stage separation.
Let's switch to the visualization. Maybe we'll see it there. Notice you can see Mars on the corner there.
We have indication that cruise stage separation has been confirmed by the spacecraft.
Okay, it's happened. So we have cruise stage separation, the first stage.
In a minute, Perseverance's landing software will wake up and begin the final preparation.
In about 10 minutes.
The first action it will do
we'll
is
hit atmospheric entry.
Entry thrusters. These pulses ensure that the spacecraft gets the thrust that it wants during entry interface. We're about 9 minutes from entry interface.
So 9 minutes until entry. Maybe we should talk a little bit more about some of the signs on board the spacecraft.
It's turning itself in the direction of...
There we go. So another instrument on the spacecraft is an interesting one that you may have seen in some crime dramas here on Earth. It's called RIMFAX. RIMFAX, let's switch to my slides here. There we go. RIMFAX actually is not an acronym. It comes from a Finnish word from Hrimfaxi, which is a horse in Norse mythology that faithfully brings the night. This is going to bring the first surface ground penetrating radar to Mars. RIMFAX is the first ground penetrating radar to be carried on any rover or lander to Mars. So these radar systems have been used by orbiting spacecraft, but we've never actually put one on the surface. And it'll offer us higher resolution data for the surface, the layers that occur underneath the surface of Mars, maybe allowing us to see layers of ice also underneath the surface. So here's a kind of a cutaway of the surface, and you'll see there on the right-hand side the what you see in the radar, opposed to the actual undersurface stuff in the left-hand side. The instrument itself, not so impressive to look at, just a kind of a golden box. And the antenna is located on the rear of the rover underneath the power source for the rover, the MMRTG, the Multi-Mission Radioisotope Thermoelectric Generator. Again, nice acronym. By far the longest acronym scientific instrument on Perseverance is SHERLOC. It stands for Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals. That is a long, acronym. SHERLOC is located near Pixel on the robotic arm, and it's going to look for elemental chemistry. SHERLOC looks for organic minerals and molecules. And if while in the presence of organic molecules, knowing them that they're there, that helps scientists to determine which samples to collect for the future return to Earth. The presence of those minerals will be revealed because the instrument on SHERLOC has an ultraviolet laser that it will scan the surface with. And it will actually be able to hunt for sand grain sized clues in Martian rocks, and it'll work in tandem with a camera. You see there that camera in the middle. This is SHERLOC, and the camera in the middle is called, yes, Watson. That'll take close-up pictures of the rocks and textures. Watson actually is an acronym. You ready for it? It's wide angle. I have to read it from my laptop here because it's too long for me to remember. It's Wide Angle Topographic Sensor for Operations and Engineering, Watson. And together they're going to study the rock surfaces, mapping out the presence of certain minerals and organic molecules. So that may contain the carbon-based building blocks for life. Here's a photo done on Earth, of course, of what SHERLOC might see. Each color there represents a different mineral detected on the rock's surface. It has a set of calibration targets. These were very well calibrated on Earth. The top row there, the center one in the top row, is actually a slice of a Martian meteorite. In other words, this was a sample of Mars that got blown off of Mars, probably by an impact from an asteroid or a meteor, and that material arrived at Earth as the form of a meteorite. We actually have a slice of Martian meteorite right here. I can show you. It might be a little hard for you to see here, but inside here, underneath this magnifying glass, there's a sample of Martian meteorite. I can actually reach my finger in and I can touch the surface of Mars here. If you come to the museum, we'll have this ready to go for you to touch Mars as well. That Martian meteorite that they're using looks something like this. And that calibration plate has not only at the top a set of things that are very well calibrated for Sherlock to look at, but on the bottom it has a lot of spacesuit materials, coated Teflon material, Teflon, ortho fabric, Vectran. These are all materials that are made into spacesuits, and polycarbonate, which is what they use on the visor for the spacesuits. And they want to see how long and how these last in the Martian environment, because the Martian environment is harsh. It gets moderately warm during the day, as high as about 70 degrees during the day, but during the night it gets down to minus 90 degrees. So they want to see how this material will respond to not only the Martian temperature changes, but also dust on Mars, and there's a lot of interesting chemicals in the Martian surface as well. So another experiment was SuperCam, and this one's really interesting. SuperCam is actually not an acronym for anything. SuperCam is the camera at the top of the mast, and here you see it sitting on the table in the lab. The SuperCam is a laser-toting robot that can study mineralogy and chemistry from about 20 feet away. SuperCam packs what would typically require several sizable pieces of equipment into something no bigger than a cereal box. It fires a pulsed laser beam out of that large circular window there, and it will vaporize small portions of rock on the Martian surface, providing information that will be essential to the mission's success. Here it is on the mast itself. There is a small microphone on the mast as well that will record the sound of the laser hitting the rock on the surface, and by recording the sound of the zaps on the surface, they will be able to tell something about the hardness of the rock. There's also a laser retroreflector on the deck of the lander, of the rover, and there you can see in the red square right there. That is will reflect lasers that can possibly be sent to it from orbit, so they can actually really carefully calibrate exactly where the rover is on the surface of Mars. Now, those sample tubes that we saw on the rover are very, very sterile, and they're used to here is you're seeing the arm now position itself to drill. This is obviously down at JPL in the lab. And it can drill samples, and here he's just handling the sample itself, but it will deposit it in the rover. And let's go back to Eyes on Mars, Eyes on NASA rather, and we might want to move the, maybe we can get Kale to move our viewpoint around by dragging a little bit so we have it in the frame. Look around, where are we? Oh, okay. There it is. We're plunging, we're in interface now. We're about to plunge through into the atmosphere. We're having a little trouble there. Let's go back to the control room, and maybe we can hear what they're going to say.
We are 1 minute from entry interface.
So it looks like 55 seconds until they enter the atmosphere. And we'll work on our Eyes on Mars visualization.
MROs are in receive mode.
We have confirmation that the Mars Reconnaissance Orbiter is now relaying data from Perseverance. We're about 30 seconds from entry interface. Perseverance is going about 5.2 kilometers per second and is about 190 kilometers altitude above the surface of Mars.
Confirm your jet data flow.
Okay, we're about 15 seconds from the beginning of our 7 minutes of terror.
Seconds from entry interface. 5.3 kilometers per second and an altitude of about 150 kilometers from the surface of Mars. We have confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second at an altitude of about 120 kilometers from the surface of Mars.
So we're officially into our 7 minutes of terror. It'll begin heating up
is
now.
now waiting until it begins feeling the atmosphere of Mars to slow it down. Once there is enough atmosphere, it will start controlling its path to the landing target.
The aeroshell can actually fly and
Navigation
navigate
is
in the
also
atmosphere.
confirming that we can see a little bit of that slowdown of the atmosphere on the Perseverance entry capsule. Our current velocity is about 5.36 kilometers per second and an altitude of about 67 kilometers from the surface.
We are probably seeing MRO plasma blackout at this point.
The vehicle should be doing its turns right now.
MRO has lost lock.
Perseverance. We have indications that Perseverance is now performing bank reversals in the atmosphere. These are the steps in order to control its distance to the landing target. Perseverance has just passed through the point of maximum deceleration and has indicated that it felt approximately 10 Earth Gs of deceleration.
MRO has lock again.
Yes, 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 yes.
We saw a small outage of the UHF telemetry from Mars Reconnaissance Orbiter during that peak heating phase, likely caused by the plasma blackout. Perseverance is still continuing to perform bank reversals in the atmosphere to control its distance to the landing target.
We're a couple of minutes from parachute deployment.
Perseverance is going about 1 kilometers per second at an altitude of about 16 kilometers from the surface of Mars. We have entered heading alignment, which means Perseverance is no longer trying to control the distance to Mars, but to the target on Mars, but instead is flying straight to the target.
Parachute.
Our current velocity is about 550 meters per second at an altitude of about 15 kilometers from the surface.
MRO is reporting good telemetry lock.
We are coming upon the we are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Yes, yes, yes.
The navigation has confirmed that the parachute has deployed and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Well, that's great news. The parachute has deployed. You noticed everybody was clapping there. The heat shield should separate.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated.
Yay.
This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
We'll eventually get to see the video of this landing from the viewpoint of the lander and viewpoint of the sky crane as well. It'll take some time to send all that video back, though.
Yes, yes, yes.
Perseverance now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers of the surface of Mars. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers. We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
That means that the lander knows where it is. It can fly to where it needs to be. It has maps stored away in the lander.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN Safety Bravo.
Okay, the sky crane is now rocketing the Perseverance down to the surface.
Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver.
We've lost direct to Earth tones.
As expected. As expected.
Sky crane maneuver has started.
Craft is now
About
being
20
lowered.
meters off the surface.
And now we're just waiting to see if it touches down.
We're getting signals from MRO.
UHF is good.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life. At this point, the descent stage has flown away to a safe distance. Perseverance is continuing to transmit direct through Mars Reconnaissance Orbiter to Earth.
You are looking at some very happy people down at JPL right now. Perseverance is on the surface. Its signals are being relayed through the Mars Reconnaissance Orbiter, which is passing overhead right now. There are several satellites that they can use to relay the signals back in that bent pipe mode.
All right, all stations.
So I'd like to thank you all for coming to our webcast here at the Exploratorium for this presentation of Countdown to Mars. I'd like to thank everyone here today behind the scenes, Cale and Rick and Wayne, that made this webcast possible, and to our partner, NASA, for such pioneering vision and execution. I'm your host, Ron Hipschman, and we'll be seeing you in further Mars webcasts coming from the Exploratorium in San Francisco.